students, I welcome you all for the physics class. Okay, last class we have studied about the PN junction diode. Okay, and the PN junction diode that can be used in the forward bias as well as the reverse bias. So the VI characteristics curve of the silicon diode we are going to see. V is a potential difference across the diode, and the I, the current which is allows in the diode across the diode is VI, that is voltage current characteristics of silicon diode. Okay, already we know the voltage is always taken in x-axis and the current is taken in y-axis. Okay, so the PN junction diode is used in a two-way. One is it is operated under forward bias. The second one is reverse bias. So there are two bias of the diodes, forward bias and this reverse bias. First, under the forward bias, from 0, the voltage is applied across the diode, that is a PN junction diode. So when a voltage is increased, there is no change in the current found under forward bias. Now we are going to see only the forward bias case. So under forward bias, the applied voltage across the diode is given, but the current is almost negligible, but not to 0. But gradually increase the applied voltage. You can notice that to a certain applied voltage, the current is exponentially increases. Okay, so till 0.6 voltage, the current is relatively negligible. But further you increase from 0.6, that is from 0.6 to 0.8, in between the 0.7. At 0.7, 0.7, this is for voltage for silica diode. Okay, so we are used only silica diode. So for a silica PN junction diode, from 0.6 to 0.8, that is at the voltage of 0.7 voltage, the current is exponentially increases. So here it offers very low resistance. So under forward bias, it offers relatively low resistance. So the current is exponentially increases. So this is the case of forward bias. But now we are going to do the reverse bias. But before doing the reverse bias, how the circuit looks we'll see. For a forward bias case, to a certain applied voltage, the current suddenly increases. No. So under which voltage, under which applied voltage across the diodes, the current is increased. So that voltage is called threshold voltage. So this is the threshold voltage. Okay. So VT stands for threshold voltage. Or it is also called cut-in voltage. So VT means the threshold voltage. It is different for the different semiconductor. For germanium, this value is very less, that is 0.2 voltage. If we use a silica diode, the voltage is high, that is 0.7 voltage. So for the forward bias PN junction diode, it looks like this. This is a PN junction. The voltmeter is always connected across the diode, whereas the P side of the diode is connected to positive terminal and the N side of the diode is connected to the negative terminal with the low resistance, and the ammeter is connected in series with the key. Okay, so this is voltmeter, this is ammeter, but the ammeter is measured in milliampere. Okay, so in a PN junction forward bias, the P side should be the positive and the N side should be negative. Voltmeter is always connected across the terminal. So this is for a forward bias case. But in a reverse bias, we should do a small changes. Instead of the positive terminal, we are going to reverse the terminal. Okay, so battery terminal should be reversed for a reverse bias case, in which, look at the diagram. This is a PN junction. For a PN junction, the battery terminal to the P side is negative, whereas N side is positive. Through a load resistor and a key and ammeter is connected, but it's a special ammeter. We need to change ammeter also. But here we used milliammeter. In a forward bias, we used milliammeter. So it is measuring milliamps. But in a reverse bias, it is microampere. Because PN junction diode that allows current only in one direction, that is mostly in forward bias. Okay. But in a reverse bias, what will happen from the circuit? The P side is negative and the N side is positive. Then once again repeat the experiment, what is going to happen? So gradually increase the upright voltage. You can notice that parallelly the current also increases up to a certain value, but further from applied voltage, the current is exponentially increases. So from 0 to 60, it is almost saturated, but it is forward or reverse. It's a reverse case, so we can say it is a reverse saturation current. Reverse saturation current. But there is a certain applied voltage. The current is for a certain applied voltage. The current is suddenly increases. No. So under which voltage the current is suddenly increased? So the particular voltage is called breakdown voltage, that is VBR, which means breakdown voltage. The breakdown voltage also differ for a different substance. For a silicon it have one value and germanium another one value. So this covers VA characteristics of silicon diode for both forward bias and reverse bias. But only one thing we should notice, under forward bias it offers relatively low resistance. But in a reverse bias, it offers very high resistance. So from this we can conclude that the junction diode can be operated only in one bias, that is mostly in forward bias. The reason is the forward bias that allows the current to pass through. Because in a reverse bias, the current is very, very less, that is in microampere. So it is almost less compared to the forward bias. Forward current is milliampere and the reverse current is in microampere. Okay. And from that, we can also find the dynamic resistance. So what is the dynamic resistance? The dynamic resistance is the ratio between small change in applied voltage across the diode to the small change in the current in the circuit. So this is a dynamic resistance. Also, the forward resistance also we can find it. The forward resistance also very less. Already I told it offers very low resistance. No, so the forward resistance, the resistance in forward bias, which is also equal to ratio between change in the applied voltage, small applied voltage, to the change in the current. So this is the dynamic resistance as well as the forward bias resistance. Now we are going to see how a junction diode used in a different appliances. Mostly it is used as a rectifier. So what is the rectifier? PN junction diode as a rectifier. Okay, so far we have studied about the PN junction diode that is operated only in one bias, that is forward bias. So the PN junction diode which allows the current only in one direction, that is in a forward bias. So what is a rectifier? A rectifier is nothing but the circuit which is used to rectify the voltage. Mostly we give the AC voltage only to the diode. So a rectifier is nothing but to rectify AC voltage across a given diode. So the circuit used is called rectifier. So for the function, the circuit used to rectify the AC voltage across the diode is called rectifier. So there are two types of rectifiers there. One is a half-wave rectifier, another one is full-wave rectifier. First we are going to see about the half-wave rectifier. Half-wave rectifier. So for a half-wave rectifier, how the circuit is used, we'll see. For that, we must need a transformer. This is a transformer. And the transformer, this is a transformer used. And here, this is AC voltage is given. AC input through a transformer. So this segment is called transformer. It's ordinary transformer. So what is a transformer? It is used to step up or step down the given voltage, input voltage. Okay. So it's a primary coil and this is a secondary coil of the transformer. Okay. So from the transformer at a point, here a diode is used. This is PN junction diode. Here a load resistor is connected across the terminal. This is a load resistor and this is a diode D at a point A and this is at a point B. So it goes like this, AC input. Okay, so this is a diode and this is a load resistor. So from the load resistor, the output is taken between the points X and Y. Okay, so how the half-wave rectifier is used? So what is the half-wave rectifier? We know in the circuit, it's a very simple circuit. So we must have the following things. One is AC input voltage. AC voltage that changes the polarity at every half rotation, we know that. Okay, so the AC input voltage is given through a transformer to the diode. Then the transformer that allows the current to the diode at a point through the point A. So the positive reach the diode and the remaining reach to the second point B. Then the output voltage is drawn across the terminal. So how the output voltage looks? Listen the graph. So from this, so at a point A, the waveform. So the wave at A, it's an input, no? So the input voltage. So this is voltage, this is time. This is also voltage and this is time. So the input voltage is given. So when an input voltage is given, that is AC input. A AC input is given. So the AC input means at every half rotation the polarity is reversed. Okay. So this is AC input through transformer to the diode. But the output is drawn from the diode, that is across the diode with the load resistor. So from the load resistor only we will get the output. But what happened, how the output looks? See. So the first half cycle there is no change. So as usual we get. But in a second half cycle is cut because we used only one diode. So the second half cycle is missing. Okay. Because if there is another one diode, then we may get it. But only one diode is used. So the second half cycle is missing. Again, the second when second full cycle, first to full second cycle will get the same peak. So same like will get at every half cycle first. So only one cycle survives, other cycles won't be there. So this output is half cycle output. So this is output across the load. Mostly like this, a single diode cannot be used in any electronic device. There is no use of it because we must need a uniform output, but this is a discontinuous. Okay, so this case cannot be used in any electronic device. So we must do some modification in this half-wave rectifier. So to get the uniform output, that is unidirectional current, what are the changes you are going to do? Only one simple thing. Another one diode is you are going to use, and the transformer circuit also changed. That is a center tap transformer. Listen. The second one is full wave rectifier. So how full wave rectifier is used or operated? So full wave rectifier. In a full wave rectifier, the same AC input is given. This is a transformer. So from the transformer, we have two diodes. Diode D1, another one diode D2, and a center tap transformer is used. With that, the output load is drawn. So from the terminal, that is load resistor is drawn. So this is output, and here the input is AC voltage as usual. This is input voltage, and this is called center tap transformer. There are two diodes are used. This is diode D1 at a point A, and this is diode D2 at a point B. Then across the XY, the load is drawn out. So the output is drawn across the load resistor. Okay. So this is a full wave rectifier circuit. How it is operated? In some cases, for using a center trap transformer, we must draw a bridge rectifier. How a bridge rectifier looks? Listen. Instead of this, we may use a bridge rectifier. This is how a bridge rectifier looks. Further, we must use a 4 diode. So diode D1, diode D2, diode D3, and diode D4. So this is called a bridge rectifier. So the bridge rectifier must be used in a center trap transformer, particularly for a full wave rectifier. Okay. Now the function, how the AC input is changed to uniform DC output. This is a AC input, but the output should be unidirectional. So how to get this unidirectional current? First, diode at a point A, what will happen we'll see. So look at the graph. Okay. So wave at A. A means the diode D1, no? Wave at A. And this is a wave at B. And this is output across load resistor. Okay, output across load resistor. First input is AC input is given. So due to the AC input, okay, AC input is given to the diode D1. So the waveform at A will be alternating. This is waveform at A. Similarly, waveform at B is connected across, no. So the waveform at B would be opposite. Okay. And the final output across the load resistors, how we'll get means, okay, in this combinations, we must connect a capacitor. Okay, a capacitor also used to connect in this cases. So we'll draw a diagram for that. With rectifier, to get the proper uniform output, we must need, see, this is a rectifier. For the rectifier, AC input is given. Then to get the output across the load resistors, we must connect one more thing, that is a capacitor. A capacitor is connected across the load. So we can say it is LC combination of L, the inductor coil, C is a capacitor. LC combinations. So here we'll use one term, is a time constant. What is the time constant? Time constant is nothing but, so the time constant is nothing but the rate of voltage across the capacitor. The rate of voltage across the capacitor is inversely proportional to the product of the capacitance value and the load resistance. Okay, so this is called a time constant. So with the time constant, the output across the load resistors would be uniform. How we get uniform means, in a first half cycle there is no change. In a first half cycle there is no change, but in a second, which means the capacitor is getting charged. So this is due to the diode D1. This is due to diode D1. Okay, and in the second half cycle, what's going to happen? In the second half cycle, the capacitor is there is no current, because diode that allows current only in forward directions. So to the maximum voltage, we will get the maximum current. But in a second half cycle, the resistance is very high, so there is no possibilities. But another one diode that is used to operate by the charged capacitor. The charged capacitor begins to discharge, and once again it needs a maximum voltage value. So this is due to D2. Similarly, one cycle over, and again this is all due to D1. This is all due to D2. Okay. So this both is combined, and again in a second half cycle, the diode D1 with the capacitor is charging, and the diode D2, the capacitor begins to discharge, and the output is delivered uniformly. So likewise, we get a unidirectional current. Okay, so this is the output drawn across the diode combinations. So the AC voltage is rectified into DC output. Okay, therefore, whatever mostly the AC voltage is given to the rectifier circuits that rectify the voltage from AC into DC. So we'll get the smooth uniform output. To get the smooth uniform output only, we'll use a capacitor. So what is the role of the capacitor? So it is used to filter the ripple. What is called the ripple means a small change in the waveform. So the capacitor that filters the ripple, that is a small change in the waveform. That's what a capacitor is connected across this circuit. Okay, parallelly. So by the about the LC combinations you're going to learn in the first volume, 7th chapter, AC lesson. You're going to learn LCR, then RMS root mean square value, then current of the root mean square, then inductor, capacitor, resistor, everything. At the time you will be very clear how this capacitor works. But here simply I said the capacitor connected across the circuit to filter the AC ripple. Moreover, to get the smooth uniform DC output. Also, to get a smooth uniform or unidirectional output. Unidirectional output, we have the capacitor combinations. So within the time constant is that plays an important role. So a time constant is nothing but the rate of voltage across the capacitor is inversely proportional to product of the capacitance value and the low resistance value. Okay.